everybody, welcome to Statistics and Theory. In this video I'm going to introduce artificial neural networks. Artificial neural networks, as we have briefly discussed in this book called Quantitative Data Analysis for Language Testing Volume 2, is a kind of nature-inspired data mining technique, or to use another terminology, it's a kind of machine learning technique. Other nature-inspired data mining methods include classification and regression trees and evolutionary algorithm-based symbolic regression. And this is not an exhaustive list, by the way. There are a lot more than these models. We have discussed artificial neural networks and their application in language assessment in this paper, which was published in Educational Assessment in 2016. I'll leave the link in the comments box for you in case you're interested to learn more about it. And also, more extensively in this CAMLA, or Cambridge Michigan Language Assessment Working Reports, which Professor Christine Go and I wrote in 2014. And the title is Predicting Listening Item Difficulty with Language Complexity Measures. We compared classification and regression trees with artificial neural networks and another model called ANFIS. In this presentation, I'm interested to see whether using the test scores of students can predict their so-called secondary school streams. The data is from an extensive data set that was collected by the team of Dr. Melvin Chen in Singapore in a project called CORE 2016. So I'm using that data. And what you should know about this data is that there are 3 streams in Singapore in secondary schools. One is called normal technical, number 2 is normal academic, and the last one is Spss. And I want to see if these test scores can predict whether students belong to Spss, normal academic, or normal technical. So I go to Analyze, and under Analyze, I'll go to Neural Networks, and then multilayer perceptron. There are 2 types of neural networks available in SPSS, and the first one is multilayer perceptron, the other one is radial basis function. For most of the analysis I've carried out in the past, I've found that multilayer perceptron has more effectiveness and accuracy than a radial basis function. So I'm going to do this, use this for the presentation that I'm demonstrating in this video. Okay, I'm going to reset this. Reset the current tab. My dependent variable, as I mentioned before, is stream. In this case, stream is a categorical variable. Your dependent variable could be both categorical or continuous. In this presentation, I'm going to use only a categorical one. Now, your predictors can either be factors, which are categorical, or covariates, which are continuous variables. So covariate, unlike multivariate analysis, which I've presented in previous videos, does not mean that you will be controlling for the effect of these covariates on the mean of your dependent variable. It's a different concept. It simply means that your predictor is continuous. So my predictors in this analysis include grammar, vocabulary, comprehension scores, and situational writing scores, as well as the PSLE aggregate score. This is another test that students are supposed to take in Singapore before entering secondary school. And I want to see if the test scores that they have gotten in these tests, which were administered to them in secondary school, can predict their stream better, or their PSLE scores. Of course, if you're familiar with the schooling system in Singapore, you would probably immediately say, of course, I would expect PSLE aggregate scores would predict secondary school streams. Now let's see if that assumption is correct, according to this data. So I'm going to move everything to covariates. Next is partitioning. In artificial neural networks, you are emulating an analysis like regression analysis. You have an output and a set of inputs. An output is your dependent variable. Inputs are your the output is the dependent variable, and the input is your independent variables. I hope I got it right. Now, in this kind of analysis, we're supposed to create two smaller samples from our data. One sample is for training, and the other sample is used for testing. During training, we create some sort of mathematical relationship between the input and the output. And then those mathematical models or rules are then used on the sample or the test sample, the validation sample, which has been held out and has not been used for training. In a sense, therefore, the test sample is an unseen sample which has not been seen by our algorithm. So after the algorithm figures out the relationship between the input and the output in the training sample, we would then like to see whether that relationship that has been figured out can predict input and output in the test sample as well. So if it can predict it, then that's evidence for the validity, like quantitative validity of the rules that were created in the training sample. I'd like to go back to my report that I pointed to, and before going on to the next tab in SPSS, I'd like to show you this figure. That's figure 1 in the report. In this figure, as you see, we have a 3 layers: layer 1, layer 2, and layer 3. The first layer is an input layer. The third one is an output layer, and the one between the input and the output here is a hidden one. This is where most of the mathematics analysis takes place. Those mathematical analyses take place in order to link our input with the output. In other words, to use the input to predict the output. So these mathematical analyses are basically simple mathematics, as many scholars say. But when you put them together, the power of those simple mathematical functions that help us to predict input from to predict output from the input will become extremely more than just a simple function. So it's like the accumulative power of those mathematical functions that makes the artificial neural networks quite unique. If you have one input layer, it's still an artificial neural network. Now, if you have two input layers, as I will show you, you start to get a simple form of what they call deep learning. So basically, deep learning, in other words, refers to an artificial neural network that has got two input layers. In this analysis, in this figure, I only have one input layer. Now, I would like to show you how one input layer and how two input layers work. In the first analysis, I would just use one input layer, and the second follow-up analysis, I would use two input layer to make it look like a simple deep learning problem. The last thing I would like to say before moving on to the next tab here is that most often 70% of the data goes to training and 30% of your data goes to testing, as you see from this box here. If you like, you can actually change it. For example, you can change 8 and then 2, etc. But I would like to just reset it to the default, because this is what many scholars in this field agree upon. For architecture, like I said, we just want to use one hidden layer and leave the rest of these options as default. But before I move on to the next step, I would like to suggest that you can keep testing different activation functions and for input and activation functions for output. These are basically the mathematical functions I was referring to. And then compare the fit statistics of the models that are presented later and choose the best model among them. Okay, for training, I'm going to stay with batch training. For output, I would like to choose a diagram, because the diagram will show you how many layers we have, and it actually makes the analysis cool. And if you like, you can get synaptic weights. Synaptic weights are these W's as you see here, and they're weights that they're simply something like beta regression coefficients, but they're actually simpler than them. I would like to get model summary, classification results, ROC curve, and predicted by observed chart, and I go through them in the output. I'd also like to get the independent variable importance analysis. I'll explain these later. Under save, I don't want to save anything for the time being, and under option, I'm going to leave everything as is. So we're going to start a very basic analysis using multi-layer perceptron artificial neural networks. I'm going to click OK, and here are the results of our analysis. This is the layers that I was referring to. We have an input layer, and as you see, only one hidden layer, and the output layer. The reason why I say that we have only one hidden layer is very obvious now. And it's hidden in the sense that we don't really know the mathematics that was taking place inside these neurons. These are called neurons, by the way, to connect the input to the output. The outputs are three, as you remember. There are three streams, so stream 1, 2, and 3. Okay, now the model summary is here. Under model summary, you will have this sum of square errors, which is pretty small. How do we know it's small? We should look at the percent incorrect predictions, which in this case is only around 5%, which is pretty low. That means we've achieved 95% of accuracy in our training. Now, whatever mathematical models were figured out in this training stage were then used to see if that mathematical model can be confirmed in the testing sample as well. And as you see, the percent incorrect prediction is only 6.6%, which means we've achieved around 95.4% of accuracy in our testing, with a sum of squares error of 23.481. So I would assume that this is really a pretty good prediction for streams. If you're interested to figure out whether the classification or you'd like to get more information about the accuracy of the classification, then I suggest that you take a look at this output. The output tells you that, for example, in the training sample, if people were in normal technical, that was 98 of them, they were also classified as normal technical. It's 98. However, there was some error as well, as you saw before. So 7 people who were actually in normal technical sample were predicted, this is the predicted side, to be normal academic, which is wrong, and only one person was inaccurately classified as the express sample. Altogether, this classification has achieved 92.5% of accuracy. And if you go further down, you see that there are different types, different amounts of accuracy. What I would like to do is to highlight this, right-click, and create a graph for them, so you will see the amount of accuracy. For example, a bar graph wouldn't be too bad. Yeah, this is our bar graph, and it basically shows the accuracy of the classification. Let's get the statistics here. Yes, good. Okay, so 92%, 88%, 97.71. This is pretty high. This is for Training Express, and the lowest one is 85%, 85.61, which is not really too bad. So the overall accuracy is 93.4 for the testing sample and 94.9% for the training sample, which is pretty good. So in this figure, in addition to the amount of error which I presented before, you will see another type of fit statistics for your artificial neural networks, One of them is specificity, and the other one is sensitivity. So sensitivity also is known as true positive proportion, and it refers to the proportion of true positives which are accurately classified as having that condition. So if you have, for example, a high number of, let's say, normal technical students who have been classified correctly as normal technical, and the same with other people in other other two streams, you would say that you would have a high sensitivity. Now there's another index here, specificity, and it refers to the proportion of true negatives which have been accurately identified as negative. For example, if someone was not express and therefore was express here is represented by the green line, and therefore was not identified by the artificial neural network as express either, you would say that, well, the specificity is likely high. Now this area, this curve is called, this, let's say, diagram is called area under the curve. And the area under the curve is very useful because just with a glance you can determine whether sensitivity and specificity were high. And we would like to have these line graphs to have a shape like this. It means there is a steep increment or increase in the amount of sensitivity, followed by a tapering off of the tail of each of the lines, which indicates high specificity as well. And this is what we would like to get in all classification models, not just artificial neural networks, but also other kind of analyses like classification and regression trees, etc. What I would like to add is that sometimes these lines, each of which represents one of the outputs in our analysis, are pretty close to this line. The closer they get to this line, the worse our classification is. And if at some point they drop below this line, then the classification is much worse than we expected, and there's no effectiveness in that. Now, the area under the curve is pretty close to 1 here, and if you're asking me how do we interpret area under the curve, here is what I would suggest. This is based on the Cambridge, Michigan report which I showed you before. For those areas that the area under the curve that are between 0.9 and 1, we can refer to them as excellent. For example, they provide the model has provided excellent classification. For those that fall between 0.8 and 0.9, we can say that classification was good. Fair is indicated by any area under the curve between 0.7 to 0.8. Poor is anything between 0.6 and 0.7, and anything below 0.50 or in between 0.50 and 0.60 is failure, and of course below that is much worse than failure. As you see in this analysis, as I said before, we have got a very good area under the curve. Now, the last thing about our analysis is the variable importance. In other words, we want to see how important each of the independent or the input variables are to predict the output or the dependent variable. And as you see, as I predicted, the PSLE score has a very high importance in predicting, and this actually is also represented in this graph. It has a very high importance in predicting our output variable with an importance of 73%. Sorry, 0.73.9, which has been normalized into 100%. The rest of the variables do not carry a very high weight, with the second one after PSLE being situational writing total score, which has around 14.3% of importance. You can take this as something somehow analogous to beta regressions in beta values in regression analysis. Okay, so that's that's an artificial neural network with one input layer. As I mentioned before, I'm going to try a network with 2 input layers, and for this I'm going to the architecture of our artificial neural network and choose 2 just to figure out how that would affect the output and the accuracy, etc. And as you see, there are 2 output layers now, so we've got something like a deep learning sort of analysis under this multi-layer perceptron modeling. The percentage of accuracy has improved slightly here, if I'm not wrong. Let me see this model summary here, and let's compare model summary. Yes, there's an improvement of around 2% or so in this deep learning analysis, because we have moved down from 6.6 to 4.4 in the testing sample. The training samples are pretty similar, with the one layer neural network being only slightly better. Okay, so let's take a look at the overall percentage of accuracy of classification. Here we've got 94.7% for training, and for testing we've got 95.6%, which is not too bad. The areas within the curve are more or less similar, at least with a very quick visual inspection you would say that they're almost the same. Now we can compare the area under the curve for the 2 models. Here we've got 0.98, 0.985, 0.994. Let me go back to area under the curve. Here, well, the differences are not that outstanding, to be honest, here. And finally, the importance variable is more or less the same, but the situational writing has lost importance in this analysis. And as you see, PSLE still is the same. The importance is more or less similar, or even the same as the previous model. So this brings me to the end of this video. I hope you enjoyed it, and if you did, please give it a like and subscribe to the channel. Have a good day.